Portland cement is the most common type of cement in general use around the world, used as a basic ingredient of concrete, mortar, stucco, and most non-specialty grout. It developed from other types of hydraulic lime in England in the mid-19th century and usually originates from limestone. It is a fine powder produced by heating materials in a kiln to form what is called Portland cement clinker, grinding the clinker, and adding small amounts of other materials. Several types of Portland cement are available, with the most common being called ordinary Portland cement, which is grey in color, but a white Portland cement is also available. Portland cement is caustic, so it can cause chemical burns. The powder can cause irritation or, with severe exposure, lung cancer, and contains some toxic ingredients such as silica and chromium. Environmental concerns are the high energy consumption required to mine, manufacture, and transport the cement and the related air pollution, including the release of greenhouse gases, dioxin, NOx, SO2, and particulates. The low cost and widespread availability of the limestone, shales, and other naturally occurring materials used in Portland cement make it one of the lowest cost materials widely used over the last century throughout the world. Concrete is one of the most versatile construction materials available in the world. History. Portland cement was developed from natural cements made in Britain beginning in the middle of the 18th century, and its name is derived from its similarity to Portland stone, a type of building stone that was quarried on the Isle of Portland in Dorset, England. The development of modern Portland cement began in 1756 when John Smeaton experimented with combinations of different limestones and additives, including tress and pozzolanas, relating to the planned construction of a lighthouse now known as Smeaton's Tower. In the late 18th century, Roman cement was developed and patented in 1796 by James Parker. Roman cement quickly became popular but was largely replaced by Portland cement in the 1850s. In 1811, James Frost produced a cement he called British cement. James Frost is reported to have erected a manufactory for making of an artificial cement in 1826. In 1843, ASPDIN's son William improved their cement, which was initially called Patent Portland cement, although he had no patent. In 1818, French engineer Louis Vicat invented an artificial hydraulic lime considered the principal forerunner of Portland cement, and Edgar Dobbs of Southwark patented a cement of this kind in 1811. Portland cement was used by Joseph Aspdin in his cement patent in 1824 because of the cement's resemblance to Portland stone. The name Portland cement is also recorded in a directory published in 1823, being associated with a William Lockwood, Dave Stewart, and possibly others. However, Aspdin cement was nothing like modern Portland cement but was a first step in the development of modern Portland cement, called a proto-Portland cement. Aspdin's son William Aspdin had left his father's company and in his cement manufacturing apparently accidentally produced calcium silicates in the 1840s, a middle step in the development of Portland cement. In 1848, William Aspdin further improved his cement. In 1853, he moved to Germany where he was involved in cement making. William Aspdin made what could be called Meso-Portland cement. Isaac Charles Johnson further refined the production of Meso-Portland cement and claimed to be the real father of Portland cement. John Grant of the Metropolitan Board of Works in 1859 set out requirements for cement to be used in the London Sewer Project. This became a specification for Portland cement. The next development with the manufacture of Portland cement was the introduction of the Rotary Kiln patented by German Friedrich Hoffmann, called a Hoffmann kiln for brick making in 1858, and then Frederick Ransom in 1885 and 1886, which allowed a stronger, more homogeneous mixture and a continuous manufacturing process. The Hoffmann endless kiln, which gave perfect control over combustion, was tested in 1860 and showed the process produced a better grade of cement. This cement was made at the Portland Cement Fabrikstern at Stettin, which was the first to utilize a Hoffmann kiln. It is thought that the first modern Portland cement was made there. The Association of German Cement Manufacturers issued a standard on Portland cement in 1878. Portland cement had been imported into the United States from Germany and England, and in the 1870s and 1880s Portland cement began being produced, such as in 1872 Eagle Portland cement was produced near Kalamazoo, Michigan, and in 1875 the first Portland cement was produced by Clay Cement Company under the direction of David O. Saylor in Clay, Pennsylvania. By the early 20th century American-made Portland cement had displaced most of the imported Portland cement. Manufacturing, ASTM C-150 defines Portland cement as hydraulic cement produced by pulverizing clinkers consisting essentially of hydraulic calcium silicates, usually containing one or more of the forms of calcium sulfate as an interground addition. And the European standard EN 197-1 as Portland cement clinker is a hydraulic material which shall consist of at least 2/3 by mass of calcium silicates, the remainder consisting of aluminium and iron containing clinker phases and other compounds. The ratio of Ca to CO2 shall not be less than 2.0. The magnesium oxide content shall not exceed 5.0% by mass. The last two requirements were already set out in the German standard, issued in 1909. Clinkers make up more than 90% of the cement along with a limited amount of calcium sulfate, and up to 5% minor constituents as allowed by various standards. Clinkers are nodules of a sintered material that is produced when a raw mixture of predetermined composition is heated to high temperature. The key chemical reaction which defines Portland cement from other hydraulic limes occurs at these high temperatures and is when the bolite combines with calcium oxide to form a lite. Portland cement clinker is made by heating, in a cement kiln, a mixture of raw materials to a calcining temperature of above 600 AA°C and then a fusion temperature, which is about 1450 AA°C for modern cements, to sinter the materials into clinker. The materials in cement clinker are alite, bolite, tricalcium aluminate, and tetracalcium aluminoferrite. The aluminium, iron, and magnesium oxides are present as a flux, allowing the calcium silicates to form at a lower temperature and contribute little to the strength. For special cements, such as low heat and sulfate resistant types, it is necessary to limit the amount of tricalcium aluminate formed. The major raw material for the clinker making is usually limestone mixed with a second material containing clay, a source of aluminosilicate. Normally, an impure limestone which contains clay or CO2 is used. The CaCO3 content of these limestones can be as low as 80%. Secondary raw materials depend on the purity of the limestone. Some of the materials used are clay, shale, sand, iron ore, bauxite, fly ash, and slag. When a cement kiln is fired by coal, the ash of the coal acts as a secondary raw material. Cement grinding. In order to achieve the desired setting qualities in the finished product, a quantity of calcium sulfate is added to the clinker and the mixture is finely ground to form the finished cement powder. This is achieved in a cement mill. The grinding process is controlled to obtain a powder with a broad particle size range, in which typically 15% by mass consists of particles below 5 I1/4 m diameter, and 5% of particles above 45 I1/4 meter. The measure of fineness usually used is the specific surface area, which is the total particle surface area of a unit mass of cement. The rate of initial reaction of the cement on addition of water is directly proportional to the specific surface area. Typical values are 320 euro 380 m2 @Ga1 for general-purpose cements, and 450 euro 650 m2 @Ga1 for rapid hardening cements. The cement is conveyed by belt or powder pump to a silo for storage. Cement plants normally have sufficient silo space for 1 euro 20 weeks production, depending upon local demand cycles. The cement is delivered to end users either in bags or as bulk powder blown from a pressure vehicle into the customer's silo. In industrial countries, 80% or more of cement is delivered in bulk. Setting and hardening. Cement sets when mixed with water by way of a complex series of chemical reactions still only partly understood. The different constituents slowly crystallize and the interlocking of their crystals gives cement its strength. carbon dioxide is slowly absorbed to convert the Portlandite II into insoluble calcium carbonate. After the initial setting, immersion in warm water will speed up setting. Gypsum is added as an inhibitor to prevent flash setting. Use. The most common use for Portland cement is in the production of concrete. Concrete is a composite material consisting of aggregate, cement, and water. As a construction material, concrete can be cast in almost any shape desired, and once hardened, can become a structural element. Users may be involved in the FAS panels, beams, road furniture, or may make cast in situ concrete such as building superstructures, roads, dams. These may be supplied with concrete mixed on site, or may be provided with ready mixed concrete made at permanent mixing sites. Portland cement is also used in mortars for plasters and screeds, and in grouts. When water is mixed with Portland cement, the product sets in a few hours and hardens over a period of weeks. These processes can vary widely depending upon the mix used and the conditions of curing of the product, but a typical concrete sets in about 6 hours and develops a compressive strength of 8 MPa in 24 hours. The strength rises to 15 MPa at 3 days, 23 MPa at 1 a week, 35 MPa at 4 weeks and 41 MPa at 3 months. In principle, the strength continues to rise slowly as long as water is available for continued hydration, but concrete is usually allowed to dry out after a few weeks and this causes strength growth to stop. Types. General. There are different standards for classification of Portland cement. The two major standards are the ASTM C150 used primarily in the USA and European EN 197. EN 197 cement types CEMI, II, 3, 4, and V do not correspond to the similarly named cement types in ASTM C150. ASTM C150. There are 5 types of Portland cements with variations of the first 3 according to ASTM C150. Type I Portland cement is known as common or general-purpose cement. It is generally assumed unless another type is specified. It is commonly used for general construction especially when making precast and precast pre-stressed concrete that is not to be in contact with soils or groundwater. The typical compound compositions of this type are 55%, 19%, 10%, 7%, 2.8% MgO, 2.9%, 1.0% ignition loss, and 1.0% free cargo. A limitation on the composition is that the shall not exceed 15%. Type 2 gives off less heat during hydration. This type of cement costs about the same as Type I. Its typical compound composition is 51%, 24%, 6%, 11%, 2.9% MgO, 2.5%, 0.8% ignition loss, and 1.0% free cargo. A limitation on the composition is that the shall not exceed 8% which reduces its vulnerability to sulfates. This type is for general construction that is exposed to moderate sulfate attack and is meant for use when concrete is in contact with soils and groundwater especially in the western United States due to the high sulfur content of the soil. Because of similar price to that of Type I, Type 2 is much used as a general-purpose cement, and the majority of Portland cement sold in North America meets this specification. Note: cement meeting the specifications for Types I and II has become commonly available on the world market. Type 3 has relatively high early strength. Its typical compound composition is 57%, 19%, 10%, 7%, 3.0% MgO, 3.1%, 0.9% ignition loss, and 1.3% free cargo. This cement is similar to Type I, but ground finer. Some manufacturers make a separate clinker with higher C3S and or C3A content, but this is increasingly rare, and the general-purpose clinker is usually used, ground to a specific surface typically 50–80% higher. The gypsum level may also be increased a small amount. This gives the concrete using this type of cement a 3-day compressive strength equal to the 7-day compressive strength of Types I and II. Its 7-day compressive strength is almost equal to Types I and II 28-day compressive strengths. The only downside is that the 6-month strength of Type III is the same or slightly less than that of Types I and II. Therefore the long-term strength is sacrificed a little. It is usually used for precast concrete manufacture, where high 1-day strength allows fast turnover of molds. It may also be used in emergency construction and repairs and construction of machine bases and gate installations. Type IV Portland cement is generally known for its low heat of hydration. Its typical compound composition is 28%, 49%, 4%, 12%, 1.8% MgO, 1.9%, 0.9% ignition loss, and 0.8% free cargo. The percentages of and are relatively high and are relatively low. A limitation on this type is that the maximum percentage of is 7, and the maximum percentage of is 35. This causes the heat given off by the hydration reaction to develop at a slower rate. However, as a consequence the strength of the concrete develops slowly. After 1 or 2 years the strength is higher than the other types after full curing. This cement is used for very large concrete structures, such as dams, which have a low surface-to-volume ratio. This type of cement is generally not stocked by manufacturers, but some might consider a large special order. This type of cement has not been made for many years, because Portland pozzolan cements and ground granulated blast furnace slag addition offer a cheaper and more reliable alternative. Type V is used where sulfate resistance is important. Its typical compound composition is 38%, 43%, 4%, 9%, 1.9% MgO, 1.8%, 0.9% ignition loss, and 0.8% free cargo. This cement has a very low composition which accounts for its high sulfate resistance. The maximum content of allowed is 5% for Type V Portland cement. Another limitation is that the plus 2, C3A, composition cannot exceed 20%. This type is used in concrete that is to be exposed to alkali soil and groundwater sulfates which react with causing disruptive expansion. It is unavailable in many places, although its use is common in the western United States and Canada. As with Type IV, Type V Portland cement has mainly been supplanted by the use of ordinary cement with added ground granulated blast furnace slag or tertiary blended cements containing slag and fly ash. Types IA, and IA have the same composition as Types I, II, and III. The only difference is that in IA, and IA an air entraining agent is ground into the mix. The air entrainment must meet the minimum and maximum optional specification found in the ASTM manual. These types are only available in the eastern United States and Canada but can only be found on a limited basis. They are a poor approach to air entrainment which improves resistance to freezing under low temperatures. Types II, MH, and II, MH, have a similar composition as Types II and IA but with a mild heat. EN 197, EN 197-1 defines 5 classes of common cement that comprise Portland cement as a main constituent. These classes differ from the ASTM classes. Constituents that are permitted in Portland composite cements are artificial pozzolans or natural pozzolans. White Portland cement. White Portland cement or white ordinary Portland cement is similar to ordinary, grey Portland cement in all respects except for its high degree of whiteness. Obtaining this color requires some modification to the method of manufacture. Because of this, it is somewhat more expensive than the grey product. The main requirement is to have low iron content which should be less than 0.5% expressed as Fe2O3 for white cement and less than 0.9% for off-white cement. It helps to have the iron oxide as ferrous oxide which is obtained via slight reducing conditions that is operating with zero excess oxygen at the kiln exit. This gives the clinker and cement a green tinge. Other metals such as Cr, Mn, T etc. in trace content can also give color tinges, so for a project it is best to use cement from a single source. Safety issues. Bags of cement routinely have health and safety warnings printed on them because not only is cement highly alkaline, but the setting process is exothermic. As a result, wet cement is strongly caustic and can easily cause severe skin burns if not promptly washed off with water. Similarly, dry cement powder in contact with mucous membranes can cause severe eye or respiratory irritation. The reaction of cement dust with moisture in the sinuses and lungs can also cause a chemical burn as well as headaches, fatigue, and lung cancer. The production of comparatively low alkalinity cements is an area of ongoing investigation. In Scandinavia, France, and UK, the level of chromium, 6, which is considered to be toxic and a major skin irritant, may not exceed 2 ppm. Environmental effects. Portland cement manufacture can cause environmental impacts at all stages of the process. These include emissions of airborne pollution in the form of dust, gases, noise, and vibration when operating machinery and during blasting in quarries, consumption of large quantities of fuel during manufacture, release of CO2 from the raw materials during manufacture, and damage to countryside from quarrying. Equipment to reduce dust emissions during quarrying and manufacture of cement is widely used, and equipment to trap and separate exhaust gases are coming into increased use. Environmental protection also includes the reintegration of quarries into the countryside after they have been closed down by returning them to nature or recultivating them. Epidemiologic notes and reports sulfur dioxide exposure in Portland cement plants, from the Centers for Disease Control, states workers at Portland cement facilities, particularly those burning fuel containing sulfur, should be aware of the acute and chronic effects of exposure to SO2, sulfur dioxide, and peak and full shift concentrations of SO2 should be periodically measured. The Arizona Department of Environmental Quality was informed this week that the Arizona Portland Cement Company failed a second round of testing for emissions of hazardous air pollutants at the company's Relito plant near Tucson. The latest round of testing, performed in January 2003 by the company, is designed to ensure that the facility complies with federal standards governing the emissions of dioxins and furans, which are byproducts of the manufacturing process. Cement Review's environmental news webpage details case after case of environmental problems with cement manufacturing. An independent research effort of AEA Technology to identify critical issues for the cement industry today concluded the most important environment, health and safety performance issues facing the cement industry are atmospheric releases, accidents, and worker exposure to dust. The CO2 associated with Portland cement manufacture falls into three categories. Source 1. CO2 derived from decarbonation of limestone. Source 2. CO2 from kiln fuel combustion. Source 3. CO2 produced by vehicles in cement plants and distribution. Source 1 is fairly constant, minimum around 0.47 kg CO2 per kg of cement, maximum 0.54. Typical value around 0.50 worldwide. Source 2 varies with plant efficiency. Efficient precalciner plant 0.24 kg CO2 per kg cement, low efficiency wet process as high as 0.65, typical modern practices averaging around 0.30. Source 3 is almost insignificant at 0.002 euro 0.005. So typical total CO2 is around 0.80 kg CO2 per kg finished cement. This omits the CO2 associated with electric power consumption because this varies according to the local generation type and efficiency. Typical electrical energy consumption is of the order of 90 euro 150 kWh per ton cement, equivalent to 0.09 euro 0.15 kg CO2 per kg finished cement if the electricity is coal-generated. Overall, with nuclear or hydroelectric power and efficient manufacturing, CO2 generation can be reduced to 0.7 kg per kg cement, but can be twice as high. The thrust of innovation for the future is to reduce sources 1 and 2 by modification of the chemistry of cement, by the use of wastes, and by adopting more efficient processes. Although cement manufacturing is clearly a very large CO2 emitter, concrete compares quite favorably with other building systems in this regard. Cement plants used for waste disposal or processing. Due to the high temperatures inside cement kilns, Combined with the oxidizing atmosphere and long residence times, cement kilns are used as a processing option for various types of waste streams. Indeed, they efficiently destroy many hazardous organic compounds. The waste streams also often contain combustible materials which allow the substitution of part of the fossil fuel normally used in the process. Waste materials used in cement kilns as a fuel supplement. Car and truck tires or Euro steel belts are easily tolerated in the kilns, paint sludge from automobile industries, waste solvents and lubricants, meat and bone meal or Euro slaughterhouse waste due to bovine spongiform encephalopathy contamination concerns, waste plastics, sewage sludge, rice hulls, sugar cane waste, used wooden railroad ties, spent cell liner from the aluminium smelting industry. Portland cement manufacture also has the potential to benefit from using industrial byproducts from the waste stream. These include in particular, slag, fly ash, silica fume, synthetic gypsum. See also. References. External links: World production of hydraulic cement, by country, PCA Euro the Portland Cement Association, Alpha the Guaranteed Portland Cement Company, 1917 Trade literature from Smithsonian Institution Libraries, Cement Sustainability Initiative, a cracking alternative to cement. What is the difference between cement, Portland cement and concrete? Aerial views of the world's largest concentration of cement manufacturing capacity, Saraburi Province, Thailand, at 14.6325 a degree N 101.0771 a degree A/14.6325. 101.0771, Fountain, Henry. Concrete is remixed with environment in mind. The New York Times. Retrieved March 30, 2009. CDC, NIOSH Pocket Guide to Chemical Hazards, ASTM C150.